A very good evening to you all. I do welcome you back to class. I welcome you back to chemistry. We are still handling chemistry inorganic. And in the previous lesson, we looked at the electronic configuration of an atom. What is electronic configuration of an atom? We looked at the various principles or rules we do follow when writing the electronic configuration of an atom. After that, we looked at how do these rules or principles apply, or how do they work. From there, we looked at the principal quantum number. We saw what is the principal quantum number, what does it indicate. We looked at what is an orbital. We used words like shell, subshell, all those ones in the previous lesson. And at the end, I did leave behind an exercise. I believe that we have all done the exercise. So I'm going to go over it such that in case you went offside or in case you did the wrong thing, you get to do corrections. So our exercise was write the electronic configuration of the following atoms. We do what? We write the electronic configuration of the following atoms. And Roman number 1, I don't recall the real order they were in, but I remember we had calcium, and calcium has an atomic number of 20 electrons. We have nickel, which has an electronic configuration of 28. We have chromium, which has an electronic configuration of 24. We have vanadium, which has an electron configuration of 23. Then we have copper, which has an electronic configuration of 29. In case there is one I have not included, you will include. So we said that an atom is made up of the various shells or the various energy level, whereby we have the S, the P, the D, and the F. We saw that the S shell takes a maximum of 2 electrons because it has only one orbital. We again saw that the P shell takes a maximum of 6 electrons, and that is because it only has 3 orbitals. Then the D shell takes a maximum of that is 5, a maximum of 10 electrons because it only has 5 orbitals, 10 electrons. Then we looked at the F shell having a maximum capacity of 14 electrons because it only has 7 orbitals. So let's start with our Roman number 1, which is calcium. And calcium has an electronic configuration of 20. So we know that we have the 1s. Let me extend this one. 2. P has 6, D has 10, and F has 14. So when we are filling, we said that we start with this is the quantum number, the lowest energy level, with the first shell or the S shell. And we say that at maximum it can accommodate a maximum number of 2 electrons. From there we go to the 2s shell, and the 2s shell, because it is still the S because it is still the S, it will take up a maximum of 2 electrons.
And then from the 2s we go to the p, that is the 2p shell, and p takes in a maximum number of 6 electrons. We count them so far, these are 4, these are 10, and calcium is having an electronic configuration of 20, so we are still remaining with the 20, I beg your pardon, with the 10 electrons. So from Aufuba's illustration of filling in the electronic configuration, this is how it goes. This is a 4s, 4p, 4d, and then 4f. So from the 2p we go to the 3s, and as the s shell, it takes in a maximum number of 2 electrons. So far we have 12 electrons, we are remaining with 8. From 3 we go to the p, and p takes in a maximum number of 6 electrons. So this is 4, this is 10, this is 12, this is 18. We are only remaining with the 2 electrons. And we have the 3d and the 4s. And from Aufuba's, the real filling would be we go to 3d with 2 electrons. But from the third principle or third rule of Aufuba's rule of filling in the electronic configuration, we saw that between the 3d and the 4s there is an overlap. There is an overlap. The 4s orbital or the 4s subshell is filled before the 3d can be filled. So that makes us have 4s come here, and s is occupied by 2 electrons. The initial one would have been 1s2, 2s2, 2p6, 3s2, 3p6, 3d2. But Aufuba told us that from his experiments he realized that there is an overlap of the energy levels. The 4s and the 3d overlap. So when they overlap, the 4s gets filled before the 3d, making the answer, the electronic configuration of calcium be 1s2, 2s2, 2p6, 3s2, 3p6, and finally 4s2. Then if you were to draw the other indicating the orbitals, you would have here, we said we first fill in that energy level, we fill in 1 electron, and after it has been filled, we come back with the opposite spin. Then here, it would still be the same case. You first fill the energy level, then you move on to the next one. Then when we come to the p, we know that p has 3 orbitals. So we write the first one, the second one, and the third one. Then we come back to do pairing, as the second rule of electronic configuration tells us. Then we go to the 1s2. We fill in the first one, then we come back and pair in the opposite and the direction. I beg your pardon, in the opposite and parallel direction. Then now we go to the 3p, which is divided into 3 orbitals. We fill in the first spin, and then we come back with the pairing. So this would be the electronic configuration of calcium. It would be the electronic configuration of calcium. Then we look at Roman number 2, that is nickel. And nickel has an electronic configuration of 28. That means nickel has 28 electrons in its outermost, that means that nickel has 28 electrons. So when we follow the same, we have 1s2, 2s2, 2p6. Because nickel has 28 and calcium has 20, so we are going to first write this one because 20 is taken in by 28. Then we see what happens after that. 3s2, 3p6, 4s2. So far here we are at 20 electrons and we still have a balance of 8 electrons. And from our Faber's principle, after filling in the 4s energy level, we go back to fill the 3d energy level. So from the 4s we go to the 3d, and we know that d takes in a maximum number of 10 electrons. So when we get those 10 electrons, but we are having a balance of 8, which means it is that balance of 8 that you are going to write here, that you are going to write there. And the electronic configuration of nickel becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8. Then let's go to Roman number 3, the electronic configuration of chromium. And chromium has 24 electrons. That means we shall also first write it like the one of calcium, because calcium stops at 20 electrons, but this one proceeds and goes ahead with 4 electrons. So we first write the one of calcium, 2s2, 2p6, 3s2, 3p6, and 4s2. So from the 4s2 we are supposed to move to the 3d orbital. I beg your pardon, to the 3d energy level. And these are 4, 10, 12, 18, 20. And chromium has 24 electrons, which means we are remaining with only 4 electrons that have not been assigned to any orbital in any shell. That means that 3D will take the 4 electrons. That is what using the principles we would get. But chromium is a very special case. Take an example that you're having a 20-liter jerry can, and then you're powering in 5, 5, 5. Then you realize that here, in this one, we are having 4 liters, while in this other one, we have 4, and then the other one of 10 liters, we have 9 liters, and here we have 2 liters. So what would you do? You have 2 liters that are in a 5-liter jerry can, and then the 9 liters in a 10-liter jerry can. Because you're selling in liters of 10, you would get these 2 liters and you first fill the 9 liters to make them plus 1, to make them 10. So that is the same case that happens to chromium. I remember yesterday I was talking about something like half filled. So this shell is very unstable, that D. It is having only 4 electrons. And the D can accommodate a maximum number of 10 electrons, which means its half would be 5 electrons. And here we are having the chromium having only 4 electrons in its 3rd energy level in the D subshell. So what happens? This S donates 1 electron to the 3D to make it 3D 5 electrons, and it becomes half filled. And when it is half filled, it is more stable. When it becomes half filled, that means the S will remain with only 1 electron. So the proper electronic configuration of chromium, from 3p6 we have 4s1 and 3d5. the fourth energy level, or in the S subshell, had to donate 1 electron to the 3D orbital such that it can get half filled and increase on its stability. Then the other one, we have vanadium with an electron configuration of 23. That means we shall also first have the one of calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. 4, this is a 2. We are having a 2, 4, 10, 12, 18, and 20. Yet vanadium is having an electronic configuration of 23. So which means the other remaining 3 electrons are those that are going to go in the 3D subshell. 3D. The balance is 3. So if you were to draw it like this one, you would find that you're having here 5 orbitals and only 3 of them are filled. Remember, we said that you first fill the orbitals singly. So you would first fill here, you fill here, and the 3rd electron stops there. And you end up with 2 orbitals that are not having any electrons. You end up with 2 orbitals that are not having any electrons. Good. We move on to the electronic configuration of copper. And copper has the electronic, has 29 atoms,